Welcome to this lecture. Today our topic is bioceramics, which basically means a group of ceramic materials which is used for biotechnology, primarily as implants in human or animal body. To introduce the subject, biomaterials in general and bioceramics in particular is one of the most active areas of research of material science in recent years. Well, the name suggests the materials used for biomedical purposes, that means the materials used in living systems. So, it is not only the ceramics which are useful for this purpose, there are other materials like metals, polymers, composites, but our discussion today is basically ceramics, because this is a course on advanced ceramic materials. It is interesting to note that the human body contains several types of tissues which are possible to be replaced by man-made synthetic materials like ceramics, metals or polymers. So, in our human body we have many different inorganic materials which can very easily be replaced by materials made by from the synthetic route. Not necessarily everything has to be synthesized within the body, but it can be synthesized outside the body and then get implanted into the body. So, all materials must attain a balance between the physical properties of the tissues to be replaced together with the biochemical effects they might have on the surrounding tissues. So, it is obviously a very challenging task, because we are trying to do something very abnormal. We are trying to introduce or replace some of the natural body components by a synthetic material which have been prepared outside the body. Of course, you have to understand what is the physical properties, what is the chemical properties, what is the biological properties, then only one can replace or use some of the synthetic materials to replace these components. But as in the very first line it has been mentioned, it is a very intense area of research, and because healthcare has become a very important aspect of human society, and therefore, wherever possible one has to take care of your ailments, the body ailments, by different ways, not only by drugs, but it also requires mechanical replacements of some of the components, and that is where the bioceramics or biomaterials in general and bioceramics in particular are very important. Biomaterials are defined as synthetic materials that induce specific biological activity and function satisfactorily in a biological environment without damaging themselves or the environment, because you are putting some foreign material inside the body, and therefore, it is very important to understand or to evaluate whether the materials themselves get damaged within the body environment, within the biological environment, or the environment gets damaged or changed by the foreign material. So, both are important. Obviously, the combination of the property requirements is diverse. You need mechanical strength, chemical durability, biochemical activity, and of course, the biocompatibility. A foreign material when goes into the living systems, it must accept it, it must not reject it. So, there has to be a amount of biocompatibility between the material and the environment in which it is put. Ceramics are known for their high strength. These are general properties of ceramics. They are normally high strength, although brittle, abrasion resistance, chemical inertness, and in some cases there are some ceramic materials, inorganic materials which have some biological activity. We will discuss that later. Now, this is a typical skeleton of a human body, and particularly the bone structure, and these bone structure are basically inorganic materials. It's certain amount of minerals are there. Of course, it is not the only the minerals. We will look into see what are the different things constitute the bone, but the whole lot of different kind of implants has been devised and has been in use for several decades now. So, whether it is a finger joint, whether it is a knee joint, whether it is a hip joint here, the details of the hip joint are like this. It is a ball and socket joint, see. So, it is the actually carries the strength, the whole weight of the body, and of course, it forms the skeleton for other components of the body. So, but it includes a fair substantial amount of our human body, the bone structure, okay. And major constituent of the bone structure is inorganic materials. We will see what is that. So, these are all different kind of tissues which a human or animal body may have. There are at least two types of tissues in human body, human or animal bodies. One is called the hard tissue and the soft tissue. Both have different varieties. Hard tissue also have different varieties, and also the soft tissues. Okay. Hard tissues, which include both normal bones and the teeth, which we have just now shown, are characterized by their high hardness, strength, and of course, the elastic modulus, because that is the basic load bearing element of the human body, and therefore, it has a different role to play, and obviously their strength is high and elastic modulus is high, because there is no plastic deformation, but elastic deformation is quite substantial, and we will see later on it is basically a composite structure. It is not a simple monolithic structure, it is a composite structure, and that is why it has so much of elastic modulus. Ceramic materials are particularly suitable for hard tissues. Ceramics as such are brittle, they have not much of flexibility, and therefore, it is the hard tissues, not obviously not the soft tissues. Soft tissues can be replaced, or a better material for better replacement for soft tissues obviously are polymers or different kind of composites. So, our interest is obviously in the hard tissues part of the body. Different types of hard tissues as mentioned. There are at least two types of bones in our body. One is called the cancellous or trabecular or spongy bones, characterized by a porous structure. Most of these bones are basically a porous structure. They are not a completely hard monolithic structures. Okay. So, one is the cancellous or spongy bone, the other is cortical bones, are characterized by highly anisotropic microstructure with much higher strength in the loading direction. Okay. So, The cortical bones have the best combination of strength and modulus, okay, the second variety. This is followed by cancellous bones like dentine and enamel. Okay. So, this so far as the strength is concerned, right. So, this is basically a composite structure. We will see what are the different components of the composite, and then you have cancellous bone, dentine and enamel, particularly related to the tooth. So, the bone characteristics, however, depend on their location in the body. Okay. All the bones are obviously not same. They have a different kind of characteristic, different kind of structures, different kind of constituents, and they perform differently. This is a typical structure, composite structure of a femoral head, that means the ball and socket joint at the hip, and it is just to show that it is a very complex structure. There are much more details. I am not going to the details of that, but basically it is a composite structure, okay, like a fibrous composites. There are 4 constituents of heart tissues. Okay. One is the collagen fiber, that is what we are talking about, the fibers, and the overall by weight is about 16%. Then you have inorganic minerals, that is the main constituent of ceramics. Okay. The hydroxyapatite, it is called the hydroxyapatite. Normally this is not this is H capital A. Okay. Right, and the compound or the very the formula which is close to this is actually Ca10 PO46 OH twice. So, it is basically hydrated calcium phosphate. Okay. It is the hydrated calcium phosphate which is the main constituents of our bone structure, about 60%. Other organics about 2% and water is about 23%. So, the relative percentage, however, varies with the position of the tissues. As mentioned, the bone structure itself changes, and therefore, the relative percentages also changes to some extent. For example, for tooth, for example, the HAP content is almost 95%. Okay. Here in general it is 60%, but in case of tooth it is 95%. Natural bones is considered to be natural nanocomposites, okay, in which collagens act as the bundle of fibers with dispersion of nanoparticles of HAP and proteins, polysaccharides, etc., acting as the cements. So, it is a very, very complex structures, and nature has done a wonder in designing this particular material. The mechanical properties are like this. Typical values for the human system are about approximately 18 GPa, the cortical bone. The cancellous bone is about 13 GPa, slightly less. Dentine is about 11 and enamel is only 0.4. Enamel, of course, is only a coating on the dentine. So, it is in general in the order of 10 to 20 GPa. That is the value for the elastic moduli. The tensile strength for the cortical bone is quite large, 135 MPa. Cancellous bone is about 52, less than half of that. Dentine is much less, and enamel is still less. So, this is more or less the property, the mechanical property of the human bones of different types. Of course, as mentioned earlier, when we are trying to replace any of these components, any of these materials or the composite material in the human body, one has to very carefully evaluate its biocompatibility. Whatever material we want to introduce into the human body, it must be acceptable by the body, the surrounding tissues, and the material should not get damaged by this tissue themselves. So, the ability of a material, this is defined, biocompatibility is normally defined as the ability of a material to function satisfactorily without any detrimental effect on the tissues surrounding it or any deterioration of the material itself. So, it may work both ways. The tissue may get damaged or the tissue damages the materials, the foreign material. So, neither is accepted. So, biocompatibility means both will be intact and both will accept each other. Three important aspects of biocompatibility is biochemically compatible. So, it is obviously within the body fluid, which is no doubt a chemical, and the body fluid must accept it. So, it must be compatible with the body fluid, the tissues as mentioned. It must be non-toxic, non-irritative, not allergenic, and non-carcinogenic. Non-carcinogenic is very important. Of course, all of them are very important. None of these variations are acceptable. Biochemically compatible with surrounding tissues, that is obvious, mentioned several times. There must be bioadhesiveness between the material and the surrounding tissues. There must be some kind of adhesiveness because that provides the strength. Without this adhesive property, the basic strength may not be developed, and therefore, bioadhesiveness is also an important aspect. There must be growth of cells on the surface. The surface must be have the right kind of environment or the properties, so the cells can grow on the surface or inside into the surface, into the crevices of the surface. Three types of biocompatible materials are available. I mean, the way they interact with the living system, we can accordingly subdivide in three different groups. One is bioinert or biotolerant materials. That means although they are biocompatible, but they do not take part in any chemical reaction with the body fluid or the surrounding tissues. So, the examples are aluminum oxide, so far as the bioceramics are concerned, aluminum oxide and zirconium dioxide. These are the two most important compounds which are used quite extensively as bioinert materials, and as we know, they are quite high strength materials also. So, wherever strength is important, these kind of bioinert materials are quite useful as implants. Whereas there is a second group is called bioactive materials. Now, the bioactive, we will discuss more about it. The examples are HAP, the hydrated calcium phosphate, and then there is a range of bioglass. Okay. It is not only the ceramics, polycrystalline ceramics like HAP or aluminum oxide or zirconium dioxide, but some of the glass ceramics. These are specific glass ceramics. 45S5 is a commercial material actually available, and this is bioglass or bioglass ceramics. These are bioactive materials which interacts with the tissues and interacts with the cell of the body, and they get a good adhesion, and therefore, they get a good adhesion part of it actually become a integral part of the body system. And the third variety is bioresorbable. Bioresorbable materials, examples are tricalcium phosphate, or in short it is TCP, or the bone cement. So, these are bioresorbable materials. We will discuss a little bit more about their properties later on. So far as the evaluation of the biocompatibility is concerned, there are different kind of tests. We are not going to the details of those, but these are different kind of tests must be carefully conducted, so that any new material becomes acceptable before it is actually put into the system. Different kind of experiments to be to test the biocompatibility are like this: cell culture, cytotoxicity assay, antimicrobial tests, genotoxicity, homocompatibility, sensitization, carcinogenicity, and implantation and histopathology investigation. So, all these, of course, for any new material to be inserted into the human body, it needs a tremendous amount of lengthy procedure, and different kind of tests must be carried out before one can really use it for any implant, whether it is small or big. These tests I am not going to the details of that. Well, coming back to the examples of bioceramics, different kind of materials normally used currently. HAF, that is your hydrated calcium phosphate. This is as a bioactive material used either as a coating on metals, okay, coating on metals like any implant which may be made of either stainless steel or a more common alloy which is biocompatible and extensively used for replacement of bones, actually titanium, or which is used for many other purposes, titanium 6 aluminum 4 vanadium alloy, or as granules. This is for so far as the HAP is concerned, either it can be used as a coating material on these metallic implants, or as granules or sinter shapes for in vivo tissue growth. Okay. So, we will discuss what is in vivo, and there is another norm which is called in vitro. So, in situ tissue growth, okay, basically one can say within the living system. In vivo is basically within the living system. So, this is a bioactive material which actively take part in the tissue culture, tissue growth within the material, within the particularly in the porous structure of the HAF. Bioactive glass I mentioned already. The specific composition is given here. Silica is about 46%, phosphorus P2O5 is about 2.6%, calcium is about 26.9%, and sodium oxide 24.6%. As you know, as all of us know, that one of the major constituents or the mineral constituents of bone is calcium or calcium oxide. So, all bio active materials must contain some calcium oxide, and that is what it given here also in the glass. It contains considerable amount of calcium oxide. This glass, when reheated, undergoes a series of structural transformation. In fact, it is not a glass, actually it is a glass ceramics, and possibly it is known that glass ceramics is different from glass. It is actually a finely crystalline crystalline ceramics within a matrix of glass. So, that is what we call glass ceramics. It is a nano composite of glass and ceramics. This is leading to crystallization, because glass is a dynamically unstable phase or unstable material which undergoes crystallization when heated, and this is the crystal or ceramic nanocrystals which comes up at around 600 degree centigrade. So, the poor mechanical property and lack of mechanically machinability limit their applicability as dental material. Although there are other materials which can be used for as a dental replacement or dental implant, but this is a very one of the first bioactive glass which was developed quite some time back, and it is being used extensively, but it has certain limitations. That is what has been mentioned here. Poor mechanical, relatively poor mechanical property. It is not absolutely useless material, it is a very much useful material, but relatively poor mechanical property and lack of machinability. That is true for most of the glasses and ceramics, but there are machinable glass ceramics also. So, if because some of it are used in dental implants, and there because of its complex shapes, machinability is an important consideration. Particulate reinforcement of this bioglass either with titanium powder, because mechanical properties is relatively low. So, there has been attempts to improve the mechanical property by these techniques, like particulate reinforcements of titanium powder, which is titanium is another biocompatible material which has been extensively used for different kind of bone replacements or bone repair. Wherever there is a fracture, titanium is one of the materials always used, but that is a metal, and so to improve the mechanical properties of the bioglass, one can use some of the compatible ceramics or metals like titanium powder, or ceramics like silicon nitride and yttria doped partially stabilized zirconia. Yttria YPSZ is yttria doped partially stabilized zirconia, improves the strength as well as fracture toughness. As you know, both silicon nitride and PSZ partially stabilized zirconia has a improved or fairly large fracture toughness compared to normal ceramics. So, they act as a reinforcing agent for the glass ceramics. Okay. The fluoride containing glass ceramics with compositions like 0.47 K2O, 0.94 Na2O, 1.42 CaO, and this kind of a composition 5.76 SiO2, 1.5 CaF2. This kind is another bioactive glass in addition to what we have discussed just now. Now, sintered shapes of Al2O3 and ZrO2 and zirconia toughened alumina. These are pure alumina, this is pure zirconia, but a combination of that is also used as a composite material, where zirconia is used as a toughening phase in alumina, are extensively used as bio inert implants as per example hip and knee joints. So, where primarily for joints which are basically need some friction and lot of movement, there this kind of high strength ceramics, relatively high strength ceramics, but inert materials are more useful. We have earlier discussed about the mechanical properties of different bones in the body. Here are some the comparison with the mechanical properties of some of the biomaterials or bioceramics in particular, which has been listed here in terms of the elastic modulus, tensile strength, as also the compressive strength. Alumina is of course a very high values, both the elastic, the tensile as well as compressive strength. Bioglass is relatively weak, obviously. HAP is also relatively weak. Zirconia, of course, it is not given here, but zirconia is more or less comparable to that of alumina. And there is one new material which has not been given discussed so much, pyrotic graphite. Pyrotic graphite is also to some extent fairly biocompatible material, but it has its own limitations inside the body so far as the biocompatibility is concerned. As you can see, alumina, although it is extensively used for a limited type of implants, because of its high mechanical strength, particularly as I mentioned joints, but it is not a bioactive or bioresorbable material. So, it does not really integrate with the tissue system so well. On the other hand, other materials, although they have a relatively low mechanical properties, but when they get integrated with this body, with the tissue systems or the cell system of this of the living system or the human body, certainly their overall strength increases. Whenever there is an implant, I think there is one has to remember that a compatibility or a comparable elastic moduli is important with the existing system. Otherwise, the incompatibility will be there and the more stress will be developed in the existing bone system than the implant. So, there is always a need for having comparable elastic modulus of the implants as well as the natural bones. Well, where all these materials can be used, for example, alumina and zirconia, the two most important areas of application is femoral head or the hip joint and also the knee prosthesis. In addition, of course, it can be used for many other joints and also dental crown and bridges. So, the list is given here: bone screws and heads, okay, to join two different components of the bone. One can use them as a screw or pins. Porous coatings are also used occasionally, porous spacers, particularly at the different joints, knee prosthesis as mentioned, and then dental crown and bridges also mentioned earlier. Advantages: inertness, this one way it is advantageous and therefore better biocompatibility, chemically they are inert, but disadvantage is less adherent to surrounding tissues because it is inert, it does not integrate so well with the surrounding tissues or the cells, and therefore possible loosening of the prosthesis at a longer time. So, there may be that limits actually the life of the prosthesis. So, if it is a bio-inert, it has its own advantages, but certain disadvantages are also there. On the other hand, which is more bioactive, which has again it has its own advantages and disadvantages. So, for some purposes bio-inert material is more useful, for other applications bioactive materials are more useful. So, calcium phosphate based, the next group is calcium phosphate or HAP kind of compounds. All of them are bioresorbable in character or bioactive also, and they use the following. They are used in the following areas of application. Let me correct that. The applications are repair and damage or the disease, repair of damaged or diseased bones, filling of voids after resection of bone tumor. There are many cases of bone tumor where the bones can be scraped off, and then to strengthen that you can fill it up with the HAP powders or porous HAP shapes. Repair and fusion of vertebra, that is also, in fact here also one can use alumina discs, but this is primarily for the repair work. Alumina cannot be used for the repair work because, as I mentioned earlier, the tissue growth does not take place, the integration does not take place, and therefore the inert materials are not good for repair. They are good for replacements, but not good for repair. Repair of maxillofacial and dental defects, well, is basically the jaw. Maxillofacial basically a jaw part. When there is a distortion in the jaw or some operation takes place in the jaw, particularly in cancer patients, you need to repair these jaws, and there these HAP kind of compounds are quite useful. In fact, not only for this purpose, repair work can be done in two different ways. One, you can use the granules and you can put them, and after some time they get integrated with the tissues, body tissues. So, it becomes an integral part of the existing system. The other is either in the form of a granule, or it can be used in the form of a injectable fluid, a viscous fluid mixed with some kind of polymers or some organic compounds. It can be delivered. It can be delivered in the form of a paste. So, there are different ways this basically bone mineralizer can be used in place. Even ocular implants, the eye, part of the eye, I will give you an example later on. A defective eye can be replaced, eyeball can be constructed actually out of the HAP material. Once again, it is a porous material, and the cell growth takes place, the tissue growth takes place, and it becomes an integral part of the body. Another very important area of the HAP or the porous systems, fine or nanoporous systems, is kind of our granules, is a drug delivery system. Drug delivery has been used for quite some time. not only with ceramics, but with polymeric. Basically, it is an encapsulation of certain specific drugs which can be delivered at the particular site. So, it is not by any kind of dissection or any kind of operation, but with the body fluid system one can deliver it, and it is possible that they goes to the targeted site. So, drug delivery is another very important area, particularly when it combines with the nanotechnology. So, nanoparticles or nanoporous materials can be used, can be filled up with some kind of drug, and they can be delivered at a particular site. So, drug delivery is a very important area of biotechnology or biomedical engineering. Porous coatings on metallic implants, it is another very important aspect where calcium phosphate based materials are used, particularly half kind of materials are used. We will see how they are coated, what are the different techniques by which this coating can be done. But metals being bioinert, whereas the HAP kind of bioactive, this combination plays a very important role. So, when we are talking about bioactivity, it is basically the surface activity which is important. So, a inert material can be always coated with a bioactive material like HAP, and one can take advantage of the high strength of the metal, the inert materials, and the surface activity of the biomaterials of the HAP. Another area I have mentioned already, but little more details of that, bioactive or surface active glass ceramics, that has been mentioned. They are capable of direct chemical bonding with the host biological tissues, once again very similar to the HAP. Only thing, their compositions are different, they are prepared in a different way. One of the advantages obviously of glass ceramics is the shaping. Shaping is little bit easier. Any glass can be shaped relatively easily in a complicated shapes or structures, which is not possible so much with ceramic materials. Their activity depends on the specific composition. There is a range of composition and mostly used for the purposes of similar to the calcium phosphate based materials. That is, and the composition, depending on the composition, their bonding capacity is different. In a ternary diagram like silica calcium sodium or soda lime silica, basically there are different areas have been identified here like A, B, C, D. Composition in the ranges of A and D have a better bonding capacity. So, lower is the content, lower is the silica content, is the better is the bonding capacity, with calcium being higher or sodium being higher. Composition B is very low reactivity, higher is the silica, reactivity with the body fluid or the tissues are low, so less bonding. And composition C somewhere in between, they are very highly reactive and so again it is not a preferred composition. So, one has to find out what particular composition is suitable for what specific purpose. Well, biomaterials synthesis, how to prepare different biomaterials. So, material synthesis in basically in the nature, this is something different. This is biomimetic materials, not biomaterials. Biomimetic materials are another group of biomaterials actually, and the way we synthesize it is almost mimicking the nature, the way the nature prepares it, because synthetic materials are prepared in a different way within the lab, whereas the same materials when they are prepared by nature, the process is quite different. So, biomimicking is to mimic the nature, and that is why a group of materials is called biomimetic materials. The material synthesized, the basic characteristics are the material synthesized in the nature's way, the way nature prepares it, we are also trying to mimic that. These are also known as bio-inspired materials. It is basically the synthesis process or the preparation technique is inspired by understanding the natural process. So, that is why they are also called bio-inspired materials. Normally a templated growth of inorganic or organic inorganic hybrid networks based on self assembly is used for this purpose. Okay. We use a certain templates, and that actually activate the process. They have a wide range of functionality which can be tailored as per requirement. Okay. One can introduce different kind of, because it is a self assembled process of some kind of a nanotechnology, and they have a wide range of functionality which can be tailored as per requirement. So, within the same material one can introduce different properties by controlling their way of synthesis, the structure developed after synthesis, or the chemical composition. Sometimes chemically gradient materials are also used, and the structures, because of the self assembly, the structures also can be tailored. So, they possess a wide range of physical and chemical properties and can be fabricated as miniature devices. So, that is what the biomimetics is concerned. Many a times they are nanocomposites displaying exotic properties. So, it is a kind of deviation or the variation of the nanosynthesis process normally, but since we are mimicking the nature's natural process, the materials made by this kind of a technique is called biomimetic materials. When we are talking about biomaterials, as we have mentioned that their test procedure is quite rigorous, and we have to go through a variety of different kind of tests before a implant can actually be used or implanted in the human body. Now, there are two very distinctive type of tests. One is called in vitro, the other is called in vivo. Okay. So, the biomaterials are often tested either in vitro or in vivo. These are the two very distinctive steps in which they have to be tested. The former, the in vitro, refers to the experimentation in absence of any living cell. That means outside the human body or the outside the animal body, or not in presence of any living cell. That is what we call in vitro test, and but maybe under simulated conditions such as simulated body fluid. SBF is a very common name in when somebody is talking about biomaterials. That is the simulated body fluid. We have in our body a lot of fluid which contains different kind of cells and organisms, and one can always simulate that in the laboratory condition, and that can be used as for testing purposes. So, that is in vitro testing. The in vivo refers to the experimentation in presence of the living cell or live cells normally used in animal models. Okay. So, one can use an animal model, animals actually, for making the in vivo tests, right. So, the animal trials and clinical trials are the two forms of in vivo research or testing. Okay. So, one is outside the living system, another is inside the living system or in presence of a living system. So, these are the two things. Once every test becomes successful in the in vitro, then one must go to the in vivo system before they are actually certified for use. Now, HAP is one of the compounds which is extensively used, and it is synthesized outside the body system. It can also be, it is being synthesized in the within the human body, but in a different way, but outside the body within the system in the laboratory it is synthesized in a completely different way. So, like any other powders, any other inorganic materials or ceramic materials, a solid state reaction, because it is a combination of different compounds like calcium oxide, P2O5, etc. So, one can use a solid state reaction at high temperature. So, one calcium compounds and the phosphorus compounds can be allowed to react at a high temperature. That is one of the simplest way to make some powders, synthesized powders, or one can use solution chemistry route like sol-gel route. Okay. So, that is also a very common technique for preparation of advanced ceramic materials. So, same thing can be used for preparation of HAP as well. Powders thus prepared are sintered at elevated temperature to prepare porous or dense shapes. Sometimes these powders are used in granules or in other shapes and sizes. So, that can be normal ceramic fabrication techniques can be used for the same purpose. Coatings on metals implants are normally prepared by plasma deposition techniques. There are many different applications where these ceramic powders are actually coated as a porous coating on metallic implants, non-porous metallic implants, and that can be done. One of the simplest way or the convenient way to do is plasma deposition techniques or plasma coating technique. In recent times, patient specific shapes and sizes of implants are fabricated by 3D modeling technique. Okay. So, a 3D modeling technique is also used for patient specific, depending on the X-ray digitized X-ray data. One can determine the shape and size, and then a section by section deposition can be used, and a specific size can be made almost not by pressing, centering, etc., but in situ centering, okay, in situ deposition and centering, not within the human body, but outside the body, and then can be implanted into the body. So, the shapes and size can be more specific and more exact in nature. As you have mentioned, biomimetic route using SBF, the simulated body fluid, particularly for the preparation of coatings. In addition to plasma deposition technique, one can use this kind of biomimetic route for deposition of the coatings as well. Well, come to the end of my discussion here. These are very specific examples prepared by Central Glass and Ceramic Research Institute, just to give you an idea what kind of implants are actually used. This is a femoral head, the hip joint, where this is a stem, what we call the stem, it is a metallic stem, and then there is a ceramic ball over there. The femoral head is basically a ball and socket joint at the hip, and that is the load bearing joint and flexible joint. So, this is the ball part, and the socket part of course is not there. These days both the socket as well as the ball part can be made of ceramics, but the stem cannot be made of ceramics. Stem is still a metallic implant, but it can be coated with the ceramics. Okay. Either normally it is coated with HAP again. This is alumina or zirconia. Zirconia can be used or alumina can be used, but here the coating, this may be primarily of HAP coating, either by plasma spraying or by biomimetic coating one can also use, but also by sol gel coating. So, different kind of coating techniques can be used, but the most convenient or useful is plasma coating. The stem can be used either of stainless steel or the titanium alloy. So, that is the general design of, there are various different designs are possible. Different companies are making different kind of designs, but the stem has to be because it needs a lot of tensile strength. Ceramic is poor in tensile strength. So, this part cannot be made of ceramics, only the ball part and the socket part, and that is most important because you need a lot of friction there. Because of the friction, the wear is more important. So, the metallic ball is not that good, but the life is relatively low, whereas a ceramic ball and ceramic socket has a much longer life. So, this is a typical hip joint prepared by Central Glass and Ceramic Research Institute. These are the X-ray patterns. This was before the operation. In fact, one person has both the joints were defective and they have been replaced by the artificial hip joints. So, this is actually the socket, here is the socket and this is the ball. So, both of them have been replaced and it has been a successful operation. Lastly, this is once again another application of HAP. This is an orbital implant. It is actually this is an orbital implant where a defective eyeball, actually defective eyeball has been replaced by HAP. It is a highly porous almost 60 to 70% porous, and it is intentionally made porous so that the tissue growth can take place inside the pores, and finally it becomes a skeleton or a composite material which gets integrated with the body or the eyeball. So, it is not an active eyeball, it is basically the filling up of the cavity, but one can make it movable. Normally the eyeballs are not movable, but in this case because of the very light weight, this is one of the very first of its kind, prepared once again by Central Glass and Ceramic Research Institute, and it is or what they call orbital implant, movable orbital implant, and made of hydroxyapatite. Once again the powders have been synthesized and made into a porous shape like this. Right. I think that brings us to the end of this discussion as well. We have discussed various aspects of bioceramics, and different forms of bioceramics, different compositions, there are different purposes and the different implants which can be made out of that. So, it is a brief discussion about the biomedical aspect of advanced ceramics. So, with this I conclude my discussion and thank you very much for your patient hearing.